Hey everyone, in this video I'm going to go through a specific use case that deals with image vectorization. So you've probably heard you can vectorize anything for use in some AI search and generative AI solutions. And in this time we're going to look at images because you can vectorize audio, video, images, just about anything. Obviously we vectorize text most of the time, but I want to just dig into image vectorization a little bit with a quick example. So let me kind of switch over to my web browser here. So this is just a quick app I built with React, and what this app is going to do. So we'll kind of like show you like what does this thing do first, and then we'll go and build it. But so I built an app that finds similar images. So for example, maybe I have an image of a person. So what I did is we'll get into it, but I vectorized a whole bunch of celebrity images. And the idea is that I can take these images. So these are images I didn't vectorize. But if I drop in just some random image of this little guy here, and then I click on find similar images, this app is going to hit a vector index and try to find images that I vectorized that are similar to this. So we'll see if it worked, and it looks like it did. So we have a Tom Cruise here. We said find similar images. We found 4 other images that are similar to this one. And if we wanted to take a different one, so we'll grab like about Sandra Bullock. I think Sandra Bullock's in here. So we'll grab a image of Sandra Bullock and we'll see if we get more Sandra Bullock. And we do. So, all right. So that's what we're going to build. Let's take a look at how we're going to do it. So first, a little architecture diagram here. So to make it a little bit more easy to follow what we're going to do next. And I'm not going to go through every detail of every one of these. I will post the source code in my GitHub repo so you can go look at it yourself. But essentially what we're going to do is, this is what we just did. So we took an image, dropped it into a React app. And then what the React app did is it searched in a vector database. So I used ChromaDB. So this is all, this isn't cloud-based at this point. This is just running on local Blackwell system that I have here. So this went into the ChromaDB and found similar vectors and then came back and showed those to me. But we had to get it working first. So the overall architecture is we have the NVIDIA, the DGX Spark, which has a Grace Blackwell GPU. I'm running Docker Compose on top of that. I do have a Llama 3.1 LLM running here. I'm not using it in this video, but it's there. And then the other things we have are ChromaDB. So this is where vectors are stored. And then we have PyTorch is running a model that I downloaded from Hugging Face called ClipVit Large. So this is an OpenAI model that will take an image, create a vector of, I think it's 760 dimensions. I don't think that's right, but it's close to that. And then stores that into the ChromaDB. And over here, you can kind of see like this is the training data it started with. So if I kind of just look at, this is the compose set that's running. So we can see we have the vector DB is running here. It's using, some resources. Overall, the solution isn't using a whole lot. So, right, 100 megabytes, 1.3 gigabytes, and 2.4 gigabytes. So it's not even really getting close to the limit on the machine. But this is the set of a compute. And let me see, what else should we look at? Let's look at the model that we're using for the vectorization. So if we take the image and we run it through the model to vectorize it, this is the model that I wound up using. There's multiples that can be used, but if we look at the model card with it's developed by research in OpenAI, and it was developed to test the ability of models to generalize to arbitrary image classification. So it's using vectors to classify images. It works pretty well, pretty easy to use, not that big. So it's pretty good. The images I'm using are from this Kaggle Dataset. So it's just a bunch of images of celebrities. So I thought that would be fun. These could be industrial images or, houses or whatever, right? So, but I used this data set because I just thought it was kind of interesting. And if we look at that data set, what I did is I split it by training and test. I just manually did that. So I brought in like of each of these, they had about 100 or so, or I think 100 of each person. And so I saved like 90 of those for training, and I saved out 10 to do testing, so I wouldn't be looking for similarity of anything of an image that the vectorizer had actually seen before. So this is what we start with, and you can kind of see like each of these is just some, mostly headshots, but some of them are body shots, but they're all of these people that we probably all recognize. So that's our data set. So this is what the embedding looks like. And I'm going to scroll to the bottom. I know it's long. So this is an image. So this image was passed in from this folder within the file system. So we kind of look back at this again. So here's the folder was Robert Downey Jr. So in this Robert Downey Jr., there's going to be this file is in here somewhere, 072. So this vector corresponds to this image, right? So we have this image. Oh, wow, he looks so young. And that image generated this vector, which is just a multidimensional representation. And when we pass in when we put a new image into the website, it's going to create another vector, and then that vector will be used to search the vector database for whichever vector in the database is the closest match for that new vector. So it all comes down to numbers eventually. That's really all these vectors really do. But this is what we're actually going to be working with. The first step we're going to do to load this, though, is I created a Python script. And the Python script, fairly straightforward. So this is just going to take a starting folder, go into each subfolder in that. It does clear the vector database, so we get rid of that. And then it's going to iterate over all the images down in all of the folders. And then here you can see it's going to create a vector, and then it's going to store the vector in Chroma. So if we look at the two functions that are in here, just real quick, we go to get embedding. So this creates the payload that endpoint wanted, and then it sends that off and gets the embedding, which is we could pass in multiple images at the same time, but this is just passing one in, so it's embedding 0 is the embedding of the image that was passed in. So here's the image base64. Here's the embedding that comes out. And then for every embedding that we get, we store it into Chroma this way. So this is going to be a post of the vector's payload, which is the image name. The topic is actually the folder it was in. And then the vector is the array of numbers. So that's pretty much all it is. And this does create a vector ID, but I don't really use it in this application, but it's good to have a primary key, right? So before we run the embedding script, let's take a look at what it's actually going to do. And it's going to pick up each of the images, which are JPEGs. It's going to turn them into base64 strings, post them to a backend API that does the embedding process and passes back an embedding. Well, let's take a look at what that endpoint actually is. So this is the backend code for the embedding server. So this is all running as a microservice. The embedding is this service within the stack, and here's the code. So what it's going to do, it's going to call the endpoint right here called v1 embeddings. It's going to pass in either a URL, which will cause this endpoint to download from the internet, or whatever web address that's located at. We're actually going to be passing in base64 strings. So this is going to load an image from the base64 string, which is kind of up here, pretty basic. So it's just going to grab the data and decode that string and then return that. Great, so that's easy. And then for each of the images it receives, and we could embed multiple images in one call. We're actually only going to do one at a time. And then this is the meat of it, though, is right here. So the processor then is going to take that image and turn that into tensors. So it's going to do some pre-processing, like resizing the image to the size the model expects and centering it and doing some things like that. And then the to device is going to then move those tensors onto the GPU. And then Torch is going to run this to actually create the embeddings. And then finally, it's going to normalize those. And that's kind of like turn it into a Python array or list. And that list of dimension values is actually what's going to get sent back. So that's what this one. So they call that normalize. So this is what that endpoint's going to return basically, is just this list right here. And then the Python script is going to put together it's going to create a UUID. It's going to combine the vectors that the vectorization service provides. So this is really long, with the original file name and the folder it came from, which we know is the name of the person. And that's what's going to be stored in the vector database. So, okay, let's go ahead and vectorize all these images and reload the vector database, and we'll see how that works. And then after that, we'll come back and just retry the service with the web app and see if it's still working. And I'm going to actually put up the NV top here so we can see how busy the GPU is. So right now the GPU it's using 51 gig of RAM on its various things, including the Llama LLM. And what I'm going to do is grab a terminal over here, and I'm going to run that script that we just looked at. So let me make that a little bit like that. And I think I ran this before, so I'm just going to run this. So this is Python main. Main is this thing we just looked at. And then I'm going to point it at the training data that has like 18 times 90 images in it. And it's just going to load them all in. And over here, we should be able to see how busy the NVIDIA box is actually doing this work. So let's go ahead and run that. And we can see the CPU is picking up a little bit. It's not much, 6%, 4%. So this isn't really even leading the system at all. The memory isn't changing because the model's loaded in RAM. It's not going to go up anymore, but we'll just let that run. And I'll speed the video up so you don't have to watch all of this, but you can kind of see what's happening here, and we'll skip to the end. Okay, so our batch load finished up and our GPU percent is back down to 0 again. So let's kind of just head over and make sure this is still working. So we'll go back here. I'll just refresh the screen. We'll get start over. And then let's grab some images and try it to make sure our vector search is still working. So Mr. Tom Hanks here. Let's see if we can find him in here. All right, similar. Hey, that looks like Tom Hanks. That's awesome. We'll just do one more. Pretty much is going to be work the same way. Oh, drill up. How about, I don't know, Jennifer Lawrence. All right, let's see what this one is. Well, I guess that was a whole photo shoot there. All right, so that's pretty much it. So what did we do? We created a vector database to store vectors in. We used a model, which is the OpenAI's clip model here. And we use that to create vectors of these images. Obviously, we didn't do traditional training for image recognition. We used the vectors to do the similarity search, and then we did our similarity search using this architecture, which is basically these two boxes. So we had our ChromaDB where we stored the vectors. We had the clip model, this creative vectors. It also is used to make a vector of this the topic of the search. Searches ChromaDB, returns top 4, and when it returns those top 4, oh, I forgot to mention, you can see the likelihood. So we do have a similarity match, so 100%. This actually was probably a duplicate, and then we have 0.94, 0.941, 0.887. So these are a little bit different, but it still says, yeah, pretty good match. And then as that finishes up, where could we take this? These images could be anything. They don't have to be faces. They could be equipment. They could be houses. They could be cars. Whatever. So hope that makes clear how this works. And I'll catch you next time.